Nice to meet you. My name is Harald Parzhuber. I'm a systems manager at Texas Instruments in a system engineering team. So when we look into system engineering, this is not within the product development, this is not within sales. System engineering is a third discipline which handles exclusive only how you build with this hundred thousands of products that are available from TI. Subsystems, and my role is within the renewable energy generation and storage area, which comprises EV charging, solar energy generation, but also energy storage. So these three buckets are under my umbrella from a system perspective within Texas Instruments. And we build basically reference designs or small system designs, which are not a complete end equipment, but are a subsystem which demonstrates the capabilities of the products to be used in an end equipment. So for example, in a solar inverter, you need a DC-DC boost. We build this and showcase that. Now back to the Electronica and what we showcased there. At the Electronica, the theme was renewable energy, and we had basically a couple of exhibitions there or demos. One was about demonstrating the connectivity and the compute capabilities we have with the products at TI. That was basically a demo that showcased a product called AM625X. Which capabilities it has from a communication perspective to demonstrate the communication from an EV charger into a car to negotiate on is it a unidirectional charging only, or is it a bidirectional operation, or is it just using the energy that comes from a solar installation and things like that. So that's the ISO 15118 communication. Power line communication into the car. The other aspect is to demonstrate with the AM62 the open charge point protocol specific layer stacks that are defined in this open charge point protocol. And here we demonstrated basically with a couple of partners, software partners, how we can achieve this and run this on the AM62 platform that we have been developing. So that was one demo that we showed there, and it demonstrated the front-end communication, back-end communication, and back-end communication. So we had multiple charging stations there, and when you plug in another 2 or 3, then charge balancing, load balancing was demonstrated and things like that. So the full-fledged capabilities of the communication and edge processing there. The other demo was more focused around power conversion systems. And within power conversion systems, this is a very important building block within the renewable energy. So what we demonstrated there was the very first building block where the grid is connected to a DC source or to a DC load. The DC source or load can be an energy storage battery system. The DC source could be, for example, a solar string converter, or the first stage after the DC-DC boost. And we demonstrated AC-DC building blocks. And AC-DC because there is power or energy flow from the grid to the sources, but also reverse. So bidirectionality was a key concern or key demonstration we showed there. And we had actually a live demo that was connecting a AC to a DC, and to demonstrate 11 kilowatt circulating power, we used 2 converters which were used in opposite method testing. Opposite method testing means one is running as a rectifier, taking the AC, generating a DC, and we connected on the DC side an inverter that takes the DC energy back again and feeds back into the AC. And there were 2 designs basically that we showed there. One was based on silicon carbide, one was based on gallium arsenide. the reason why we have been choosing these technologies, there is no battle about silicon carbide and gallium arsenide. Both have their sweet spots where they perform perfect. And at TI, we have GaN technology, 650 volt GaN technology. And for certain power levels and where form factor and high efficiency is of concern, there it fits. And we see the border somewhere at around 11 kilowatt, everything below 11 kilowatt, where size of the solution, form factor, high power density is of concern. GaN is an absolute viable solution. And that's what we demonstrated there. So we had two designs, one SiC-based, one GaN-based, and they were basically operating live at 11 kilowatt, and we could circulate actually the power. What was nice about that one, we used for the digital control in this, we used the MCU family C2000, and we were basically using also the development tool, which is called Code Composer Studio. And so this was a demo for engineers as well. So people could stop by and say, okay, can you adjust for a certain power? Can you adjust for a certain reactive impedance? And we could demonstrate that actually while people were interested to see this is not just a horse and pony show. This was a live demo for engineers to demonstrate the capabilities of these technologies. So that was what was going on at the Electronica. A lot of interest there, a lot of people that asked a lot of good questions. So we might go now into your questions, or if you have questions around these topics.
So thank you, Harald, for giving such a good introduction to what happened in Electronica. So yeah, I welcome you in TimesTech Media. So coming straight to the questions, one of the things that you mentioned was bidirectional charging. So how this bidirectional charging could be a game changer, and what innovations and development TI has made in this concept to make it more efficient and safer?
Yep. Okay, good. Yeah. So bidirectional operation is needed when you think about an EV charger that is used for vehicle to home or vehicle to grid communication. But the AC/DC stage needs to operate in both directions to enable vehicle to home and vehicle to grid, but also enable energy storage from the grid into battery systems and taking that excess energy back into the grid when there's a demand in the grid. So there are a couple of power topologies that can support that. The dumbest way you can do is basically build two converters which run in opposite direction. But there are topologies like a T-type, like ANPC. ANPC stands for active neutral point clamped. So these are topologies which can be operated with digital control, with a microcontroller in both directions. And that basically shows that enables power flow from the grid to the DC sources and back to it. The vehicle to home and vehicle to grid is something which we view as something that will come in the future to make the grid more resilient. But what is happening today already is vehicle to home, to help your home installation, your residential installation, to cope with higher excess power demand while you have a car parking in your garage. So that is actually happening today already. And we see offerings for DC wall boxes that can take the battery energy back. And T-type or ANPC topologies are perfectly suited for that. Let me come back to the small form factor again. So if you have for residential use a bidirectional converter, small form factor is of concern. You don't want to have a 100-liter box in your garage. It needs to be within the 20-liter range, maybe below that. So taking wide bandgap technologies as the power switches, like silicon carbide or like gallium arsenide, will help to operate these converters at higher switching frequencies, but still maintain a high efficiency. And what I said at the beginning, that we had GaN and SiC, this is not a battle, it coexists. And everywhere where highest power density is needed at a reasonable low power, which is below 10 or 11 kilowatt, GaN has benefits. So we demonstrated that at the same efficiency, a converter in silicon carbide needs to run at slightly lower switching frequency, which is driving the size of the components, of the passive components, a little bigger. So you can make a gallium arsenide based solution probably between 10 and 15% smaller, because you can operate it at maybe 40% higher switching frequencies. And this to achieve still the same efficiency. So let's talk numbers. We were operating both at 98.2% efficiency. One has to run at 60 kilohertz, the other one at 100 kilohertz. And that drove the size of the magnetics down. Slightly higher power, power efficiency or power density.
Yes. So are these unique products in themselves, or your competitors are also making similar kind of products?
So what we see is that there's a lot of companies looking into gallium arsenide. The reasons are relying just on one wide bandgap technology would create probably supply demand complexity. More companies looking into gallium arsenide just shows there is more room for everybody for the different requirements there. So some people say there's a battle between SiC and GaN. Our view is it coexists and both have valid value propositions to be used in particular end equipments.
So the products and innovations that you showcase in Electronica 2022 are available in the market right now, or are these in the test phase only?
No, actually what we demonstrated are all released products. So for example, we used a GaN switch called LNG 3422 R0030, which is a 30 milliohm GaN FET, but it's not just a GaN FET, it has a little bit more in it. It has a temperature sensor integrated, it has the gate driver integrated, or the bias supply for the negative biasing of the gallium arsenide FET. A little bit more integrated into that, which helps to eliminate a lot of the discrete functions like smart gate drivers, which detect overcurrent and short circuit protections. That's all integrated into that device. All that is available on ti.com right now. So nothing was an outlook. We demonstrated state-of-the-art technology here. What we also showed in all of our reference designs is for a digital control, you need to feed back voltages and currents to keep the converter in the desired operating state. For the voltage feedback, normal resistive dividers are used and operational amplifiers that feed into A to D converters, which are integrated into a MCU. The current sensing, we showed exclusive only shunt-based current sensing. And we have a product family which is released since a couple of years already, which has a very low input voltage range. So isolated amplifiers and isolated delta sigmas, which have a 50 millivolt peak input. That means you can use for a 15 amp RMS a resistor that is only 2 milliohms. First of all, it creates only within the inline current a 50 millivolt ripple, which is negligible if you compare this to the voltages that appear there. And from the power dissipation perspective, if you do the math, 2 milliohm, 15 amp RMS, this is only half a watt power dissipation. And this is just an example. For 11 kilowatt power converter, the shunt resistors just dissipate per shunt resistor half a watt in maximum load. That's negligible compared to the overall power feed through that the converter has. And it does not even count into the efficiency. We talk about 200 watt of losses in the power switches. So half a watt for a shunt resistor to measure the inline current is nothing. So that's why we demonstrated, or we tried to eliminate the rumors about a shunt-based current sensing is power hungry and it has impact on the voltages that are appearing at the current measurement points. And that's simply not true. So with the AMC 13 family and the AMC 33 family of isolated amplifiers and delta sigmas, we can go down as low as 50 millivolt and still maintain a high accuracy.
So how has been the market response to your products?
It was of course, so TI is known for the company that is doing all the signal processing, is doing all the signal chain products, has a lot of power products, but when it comes to the high power switches, people assumed TI is not playing that much in that market. But with the GaN portfolio we have, there was very good resonance, and people liked very much the level of integration that we demonstrated on the devices. As I said, the GaN devices, they have a lot of protection features integrated, a lot of gate driver and signal chain integrated into it.
So my next question is, what advancement TI has made in the efficient green and renewable energy system?
We have been basically showcasing that we are not concentrating only on the sub-functions for point of load, DC-DCs. We have been demonstrating that with the digital power control we can do with our microcontrollers, like the Citara MCU family, like the C2000 DSP family. We can build systems that are highly efficient, can be used for the renewable energy market where efficiency, reliability, and safe operation is absolutely needed. As an example, the Citara MCU family has integrated safety islands. That means you can build systems that have functional safety integrated. So we offer that possibility now as well. Historically, in solar inverters or in renewable energy, safety was a minor role, but we see more and more people taking care about SIL certified products. And that is what we can support. So these are the big achievements moving forward, that we are absolutely prepared to support functional safety requirements that are showing up today and will continue to show up moving forward.
So last question, what are the like future technologies or technological integration that we can see from Texas Instrument in area of electric mobility and assisted driving even?
So giving more compute power to the digital controllers, integrating more functionality into one MCU where it makes sense. As an example, historically, if you build a DC-DC or AC-DC, you can operate this in two separate MCUs. With the Citara MCU, which is a multi-core MCU family, we are able to basically run one function like the AC-DC on one MCU, a DC-DC boost on another one, and have one MCU that runs, for example, arc detection algorithm, which could be based on identifying signatures running FFTs. So that's where we are moving to. and that's to basically build more functionalities into the controllers and still maintaining the high quality on the PWMs. You need to control all the switches, but also still maintain high accuracy on the feedback passes for the voltages and the currents, which is crucial. Yeah.
So thank you for talking to TimesTech Media and giving your time to us. Thank you.
You're very welcome, Om. I appreciate it.
Thank you. Yeah.
Thank you, Om. Thank you, George, for setting this up.
later.
Appreciate it. Thank you.
No
And
problem.
bye-bye.
Bye.
Bye bye.